It's my philosophy as a math teacher that if I teach a way that always works and everybody can start from that foundation and then we get proficient with that, then as we see certain special cases, the kids that are more proficient with this, they're going to see the special cases and go to them. The other ones that don't see it are still going to get the right factoring answer because the basic approach works. So let's take a look at what I'm talking about. We learned in the last video that we want to go from a quadratic trinomial to making it have 4 terms and replace the linear term with 2 other terms whose coefficients add to the original linear coefficient and who multiply to be a times c. Well, what happens if we have a special case like this guy right here, x squared minus 49? Well, no problem, because what we can do is we can write this as x squared plus 0x minus 49. We can add a linear term that has a coefficient of 0 so that these two things are equivalent to each other. And we're still going to do this. We want 2 numbers, 2 linear coefficients that add up to this guy, but they multiply to give us 1 times negative 49. So they're going to multiply to give us negative 49, but they're going to add to give us 0. Well, the 2 numbers that multiply to negative 4 and add to 0 are going to be opposites of each other. 7 plus negative 7 add up to 0, but they multiply to negative 49. So what we're going to do is we're going to say, okay, let's rewrite this guy, x squared minus 7x. Remember, it's a good idea if you have a negative coefficient, let's put that one here first, and then plus 7x minus 49. There it is. We've rewritten it as 4 terms, and now it's time to divide and conquer. Now we just say, okay, we're going to take these 2 terms. What's the common factor? It's an x, so we're left with x minus 7. Let's go over here and come up with a common factor. 7 can come out of both of these, and what we're left with is x minus 7. So how many of the x minus 7 binomials do we have? Well, let's take a look. We have x of them here and another 7 of them here. So altogether we have x plus 7 of the x minus 7. There. That is the factored form of this. Okay, now, you can go through all of this hassle that we just did, and it works. And so it's like, I'm still got to be careful with my quadratics. That's fine. Use this grouping approach that we've learned. But if you can see that this is a difference of 2 squares, that what you're looking at here is x is being squared, and then there's a difference, subtraction, and 7 is being squared. If you can see that this is the difference of 2 squares, then you can immediately memorize that that becomes this right here. That it becomes whatever the squares are, it's x plus the 7 and then times x minus the 7. So as soon as you can recognize that that's a difference of squares, you can go right here to the final answer. If you don't, hey, add the linear term, everything's going to be fine. Use the approach we've talked about, you're going to get to the right answer. Let's look at a couple more special cases right here. What we'd love to get our students to do is to recognize that this is a perfect square trinomial. That because half of this linear coefficient squared would give you the constant coefficient, we'd love it if you could see that this would end up being the quantity x plus 5 squared. If you don't, the approach that we've taken is going to work because we're looking to replace the linear term of 10x with 2 linear terms that add to 10x, but they multiply, the coefficients multiply to 25. So we're going to realize that, oh, what those 2 linear coefficients would have to be, they both have to be 5. So both these are equivalent, and now divide and conquer, factor by grouping. X is the common factor of these 2 guys, 5 is the common factor of these 2 guys. So how many of these binomials, x minus x plus 5, do we have? We have x of them here plus another 5 of them here. So we have x plus 5 of the x plus 5s. Hey, that's what this is. That's what we're saying. This is a perfect square trinomial because it's the square of one binomial. Hey, if you can recognize it, since half of this squared is that guy, you can go right to this. If you don't see it, just take the factoring by grouping approach and you will get to the right answer. Likewise, you could have a subtraction sign here, but again, half of negative 6 is a negative 3, and because negative 3 squared is 9, You could recognize this as a perfect square trinomial and just go right to here. That's your answer and you are done. But if you don't see that, you're going to say, okay, I need two linear coefficients that add up to -6, but they multiply to 9. And my answer would be that both those linear coefficients would be a -3x. So we rewrite that this way, and now divide and conquer. We factor by grouping. Common factor is x. Common factor here is a -3, so be careful, this is sneaky. Let's take out a -3, so that's -3. Now what would be left is a positive x, but dividing this by a -3 makes this a -3. Or in other words, -3 times -3 gets back to a 9. Hey, here we are. How many of these binomial x minus 3's do we have? We have x of them here, minus 3 of them here. So altogether we have x minus 3 of the x minus 3's. Hey, this is that binomial squared. Either way, you get the right answer. But it'd be nice if you can start recognizing the special cases.